Welcome to Compaction of Soils Part 1. Compaction is a process in which the soil solids are arranged into a dense state by applying a mechanical energy. As you all know, the soil is widely used as a construction material. So, this compaction is a phenomena which is very much helpful in making the soil denser so that it will be able to support the loads safely. So, in this lecture we will be understanding about the compaction characteristics of soils, factors affecting the compaction behavior of a soil, and then we will try to look into the laboratory determination of compaction characteristics of soils. Then we will go into the field and we will try to understand what are the different methods available to assess the field compaction characteristics of these soils. So, let us start with in understanding what is compaction and where it is applied and all. So, in many situations soil itself is used as a construction material. As you all know, many earth-fill structures are constructed with soil, such as highway embankments, railway embankments, earth dams, highway and airfield pavements, backfill trenches, in the environmental applications landfills. So, when the soil is used as a foundation material, it is desirable that in place material possess certain properties, so that it serves the purpose of the function. So, the soil is widely used as construction material in projects such as highway embankments, railway embankments, or earth dams, or highway and airfield pavements, backfill trenches and landfills. The purpose of compaction is to produce a soil having physical properties appropriate for a particular project. This is very much important for us to see that the purpose of compaction is to produce a soil having a physical properties appropriate for a particular project. So, let us try to look into the definition of compaction. Compaction, which is defined as the process of increasing the unit weight of soil by forcing the soil solids into a dense state and reducing the air voids. So, compaction is basically a phenomena in which the expulsion of air takes place. So, compaction is defined as the process of increasing the unit weight of the soil solids by forcing them into a dense state by applying a mechanical energy and reducing air voids. So, this is achieved basically by applying static and dynamic loading to the soil depending upon the type of the soil. So, this densification is achieved by applying either static load or a dynamic load. Compaction is measured in terms of the dry unit weight of the soil. So, in this slide we have defined compaction, and which is the process of increasing the unit weight of soil mass by forcing the soil solids into a dense state and reducing the air voids. Compaction generally leads to the following desirable effects on soils, which are summarized in this slide. This slide shows first and foremost one is increased shear strength, that is the strength which is required to resist the stresses which are caused by the external loading or due to the self weight of the soil. So, this means that the larger loads can be applied to compact soils since they are typically stronger. So, increased shear strength, this means that larger loads can be applied to compacted soils since they are typically stronger. The compacted the soil mass, then larger the loads can be applied. Reduced compressibility, this also means that larger loads can be applied to compacted soils since they will produce smaller settlements. So, if it is uncompacted, then one can think of inviting settlements. So, reduced compressibility means that larger loads can be applied to compacted soils since they will produce smaller settlements. Reduced permeability, this inhibits soil's ability to absorb water and therefore reduce the tendency to expand, shrink and potential liquefy. This inhibits soil's ability to absorb water. The reduced permeability or reduced compressibility and increased shear strength, these are the effects which are generally possible by compacting the soil. That means that the soil can be increased by shear strength if you compact the soil, and reduced compressibility, it can have a reduced compressibility, and because of its compacted nature, it can have a reduced permeability. The reduced permeability inhibits the soil's ability to absorb water and therefore reduces the tendency to expand or shrink or potential liquefaction. To reduce the susceptibility of liquefaction can also be minimized. So, purpose of the compaction, to some extent we have seen that reduced compressibility, increases shear strength and reduced permeability, and the purpose of the compacting earth fills such as earth dams and embankments in highway, airfield and canal is to produce a soil mass that will satisfy two basic functions. That is whatever we have discussed. One is that reduction in settlement and increase in the shear strength. So, the basic purpose of compacting earth fills such as earth dams and embankments, particularly highway embankments, railway embankments and canal, is to produce a soil mass that will satisfy two basic criteria. One is the reduction in the settlement and increase in shear strength. Let us look into the various factors, what are the purposes of compaction. Maximum shear strength occurs approximately at a minimum void ratio, that is with reduced with the closer packing, maximum shear strength can be achieved. Larger air voids may lead to compaction under working loads, causing settlement of the structure during service. Larger air voids, suppose if you have got a soil mass and an embankment with larger air voids, once it is released for traffic loading and it is susceptible for settlements, and it can be out of the service very early. So, larger air voids may lead to compaction under working loads, causing settlement of the structure during service, and large voids if left may get filled with water and which reduce the shear strength. So, these air voids subsequently when they come across the water, the ingress of the water within the voids causes decrease in the shear strength. So, the stability of the structure will come into the picture. Increase in water content is also accompanied by swelling and loss of shear strength in some clays. So, increase in water content is also accompanied by the swelling of the, but depending upon the type of the mineral, it exhibits swelling, we have discussed in the previous lectures, and loss of shear strength in some clays. So, the purpose of the compaction we have summarized here, like maximum shear strength occurs approximately at minimum void ratio, and larger air voids may lead to compaction under working loads, causing settlement of the structure during service, and larger voids if left may get filled with water which reduce the shear strength. An increase in water content is also accompanied by swelling and loss of shear strength in some clays. What are the advantages of compaction? So, if you look into this, as we discussed, settlements can be reduced or prevented. By compacting the soil, the settlements can be reduced or prevented. Soil strength increases because we are making the soil mass denser and denser, and stability can be improved. So, this is another advantage, which is the soil strength increases and stability can be improved, and load carrying capacity of pavements or subgrades can also be improved, because the soil, if you compact more, then load carrying capacity of the pavement subgrades can be improved. Undesirable volume changes like frost action or a swelling or shrinkage phenomena may be controlled. So, undesirable volume changes like shrinkage, swelling or frost susceptibility can be kept under control by doing a compaction. So, these are the following are the advantages of compaction. One is the settlements can be reduced or prevented, and soil strength increases and increases the stability of the structure, and load carrying capacity of pavement grades, pavement subgrades can be improved, and undesirable volume changes can be kept under control. So, here in this slide, as you see, the soil along with the 3-phase diagram is shown. This bucket consists of the moist soil, W2 is the weight of the soil and Vt is the volume of the total soil. If you idealize this into 3-phase diagram, then Ws is the weight of the solids and water is in one part which is shown here, and then air which is above the water. So, Va is the volume of air voids, Vw is volume of water, Vs is the volume of solids, and Ww is the weight of water, W suffix s is the weight of solids. So, we have understood and we have seen this phase relationship in the previous lectures. Now, we will be applying into with reference to compaction behavior of the soils. So, basically if you look into it, compaction is nothing but expulsion of the air. That means that the process of compaction, once we compact the soil, what will happen is that the air which is there is will be shunted out by applying a mechanical energy, but all the air cannot be shunted out. To some extent, there is a certain relationship between this arrangement and optimum water content that will be discussing in the forthcoming sections of this lecture. So, here basically we said that compaction is nothing but a phenomena which is expulsion of air, and the air which is there which will be shunted out by with the help of a mechanical energy or any suitable method like static loading or dynamic loading depending upon the type of the soil. So, when loose soils are applied to a construction site, when loose soils are being used for a construction site, compressive mechanical energy is applied to the soil using special equipment to densify the soil. So, when loose soils are applied to the construction site, so we are using say a loose soil mass which is used for construction site, then compressive mechanical energy is applied to the soil using special equipment to densify the soil or to reduce the void ratio. Densification is nothing but the reduction in the volume of air voids. And this compaction phenomena is almost an instantaneous phenomena, and soil is always partially saturated. 100% saturation cannot be achieved with the process of compaction. So, the compaction is an instantaneous phenomena and soil is always remain partially saturated. That means that in compaction soil always remain like a 3-phase material, and typically applies to soils that are applied or to reapply to a construction site. They are already applied, say you wanted to densify further, then this particular concept will be applicable, or you are constructing a new structure, then which a new soil layer has to be compacted, then again this particular technique will be helpful. So, compaction phenomena is a ancient old technique, and it has got roots in ancient China and India. It was reported that compaction was earlier used in the construction of Greater Wall of China and in the foundation construction of the Taj Mahal in India. So, the compaction is a old technique and which has got roots in ancient China and India. So, before discussing into the procedures for determining and principles of compaction, as you all know, we have got two different types of soils: cohesionless soils or sandy type soils or gravelly soils, and clayey soils or cohesive soils. So, these two soils they exhibit a different soil structure. We all know these bulk particles exhibit the single grain structure and or to some extent to honeycombed structure. So, when speaking about cohesionless soils, gravelly soils, there are many possibilities. If you look into it, the particle can be angular and subangular in nature. They can be having in loose arrangement, that means the loose angular soil and dense angular soil. You can see dense angular soil with minimum number of minimum voids and loose angular soil exhibiting these white spots which are shown here in between, they are the large air voids. In the other case, a round uniform grains, if you consider, honeycombed soil, very loose state, exhibits voids like this. The white spots in between these uniform grains, idealized spheres, are the voids, and with loose arrangement, here you will see also this type of arrangement, single grain structure, where you will see the large amount of voids. The same situation in the dense arrangement, you can see that the less number of voids. So, when speaking of cohesionless soil, generally we have got particles shape coming to picture, where it can be loose angular, loose subangular, dense angular, dense subangular, or it can be having a mixture of particles, or having uniform sized particles in a loose state or in a honeycombed state with the honeycombed grain structure, or in a grain structure with loose state and dense state. So, soils in loose or honeycombed state are avoided or compacted, that means that they are subjected to a process of densification before being built upon, since they are prone to densification when subjected to vibratory or shock loading, as from the earthquakes or vibrating machinery. So, these loose deposits of soils are always problematic, particularly sandy type of soils or a fine sandy soils when they are saturated in a loose state, when they are subjected to a shaking either because of a blast loading or due to earthquake, they will be subjected to a instantaneous densification, in which they lose all the supporting strength, and then the structures which are resting on this soil are susceptible to failure or large settlements. So, in this, soils in loose or honeycombed state are avoided or compacted before being built upon, since they are prone to densification when subjected to vibratory or shock loading, as from the earthquakes or vibrating machinery. That is what we have discussed. So, in this slide, on the left hand side, you will see here a soil mass with a void ratio E naught, which is the maximum possible void ratio with at lowest possible density, and the initial height is H naught. Say this may be the layer thickness with H naught with the void ratio E max. So, when it is undergoing, when after subjected to compaction, say EF, which is E minimum, is the minimum possible void ratio for the particular soil. We knew that this particularly coarse grained particles exhibit the void ratios like maximum void ratio and minimum void ratio. The maximum void ratio is the one at which the density is minimum, and minimum void ratio is the one at the density is maximum. So, at this point, the delta H is the compacted thickness. So, delta H by H naught, that is delta H is the change in thickness, H naught is the original thickness, HF is the final thickness here. So, delta H by H naught is equal to E naught minus EF. E naught minus EF is nothing but E naught is the E max, which is the initial void ratio. EF is the, in this case, EF is the final void ratio, in this case it is E minimum. So, E naught minus EF is nothing but the delta E divided by 1 plus E naught. So, this is directly will give, sometimes if you are able to, if you know these void ratios, you will be able to determine what is the compacted thickness and all. So, but here it shows that soils in loose or honeycombed state are avoided, or they are subjected to process of compaction since they are prone to densification when subjected to vibratory or shock loading. So, here the relation which is expressed here is delta H by H naught is equal to E naught minus EF by 1 plus E naught. When looking into the compaction behavior of a cohesionless soil, let us look into some of these points. Like the relative looseness of a soil in its natural in situ state is determined by measuring, computing its relative density dr. This we have already studied earlier in the previous lecture. The relative looseness of soil in its natural in situ state is determined by measuring, computing its relative density dr. The smaller dr is for a given soil deposit, the more prone for the soil deposit will be to densification and settlement. The smaller is the value of a relative density, more is the prone for densification and settlement. So, it will be the particles will be rearranged into a dense state and then ultimately they will be subjected to settlements. For uniformly or poorly graded spherical grain soils, the theoretical range of the void ratios is between 0.35 and 0.90. For uniformly or poorly graded soil, the soils with identical particle sizes or basically say spherical grain soils, the theoretical range of void ratio is between 0.35 and 0.90. For non-uniform well graded soils, the possible range of void ratio is much smaller. Well graded with subangular sand, void ratio is 0.35 to 0.75, well graded with silty sand 0.25 to 0.65. So, if you look into here, the range of void ratios for well graded soils is less than that for a uniformly graded soil. So, that is why it is generally preferred to use well graded soils in geotechnical applications as opposed to uniform soils. So, that is the reason why generally we use we use well graded soils for the better construction and in order to carry the loads safely. When you look into the further into the compaction soils, the soils particularly sandy type of soils, they can be compacted only by a vibration, particularly cohesionless soils or sandy soils or a gravelly soils, they can be compacted when by subjecting them to a set by using a special equipment with vibrations. Static load pressures produce very little compaction of the loose sand. So, static load produces very little compaction to the loose sandy soils or a gravelly soils. Medium and fine sands do not get compacted easily when moist because of the shear strength developed by the capillary forces. Because we knew that medium and fine soils do not get compacted because of the presence of the shear strength which is arisen before or because of capillary forces. Dry or submerged sands can be compacted by vibration. Dry sand, either the sand in dry state or in a submerged state, can be compacted by subjecting them to vibration. So, what we learned from this slide is that it is not possible to compact the gravelly soils or sandy soils by applying static pressures, because little compression is caused, but can be possible by applying or subjecting to shaking or vibrations. This we will be seeing during the course of the lecture in the form of a small demonstration. Now, let us having discussed about the compaction of the cohesionless soils, another end of the or another distinctive type of the soil is the fine grained soil, that is clay type of soils, where the fine grained particles or a platelet particles are the predominant in the soil mass. So, clays cannot be compacted by vibration. So, contrary to this cohesionless soils or sandy soils, clays cannot be compacted by vibration. Shaking or vibration does not produce any volume change. A very small amount of static pressure produces a large volume decrease of the platelet particles like mica flakes. So, if you are able to apply a small amount of static pressure, that produces a lot of volume change than by applying a vibration to a clay mass. So, in compacting the clay, the position of the particles must be changed by forcing the contact points along the adjacent surfaces to positions of nearly more parallel with reduced voids. So, we knew that these particles will attach like to face to edge orientation or edge to edge orientations. These platelet particles have to be rearranged by applying the pressure and to the almost like a parallel positions, so that maximum change in the voids in the volume of the voids occurs. So, in compacting the clay, the position of the particles must be changed by forcing the contact points along the adjacent surfaces to positions nearly more parallel with reduced voids. That is what we are discussing. So, if you look into this particularly clay type of soil is known for a platelet typical particle is of platelet shape and which has got adsorbed water and with highly viscous liquid which is surrounding clay particle, and then which is also surrounded by a free water. That is what which is shown here. The thickness of the adsorbed and free water is depending upon the amount of the available water. This we have discussed in the particle forces lecture. So, here in this case, like a house of cards, loose structure of clay before compaction is shown here. So, you can see different clay particles attaching with edge to face or edge to edge orientations, and these are the large voids in between these particles. So, these particles can be rearranged by subjecting them to a set of static pressure. Dense structure of the clay after compaction is shown here, is almost like a parallel arrangement, where from here to here the particles have undergone a the orientation of the particles has changed from almost from 50 to 60 degrees. So, you can see here these are the voids and these are the rearranged clay particles or platelets with the application of the static pressure with the less number of voids in between these platelets. So, when the clay has a high water content which is less than the saturation, a thick layer of free water surrounds the particles. That when the clay has a higher water content less than the saturation, a thick layer of free water surrounds the particles of low viscosity. Under this condition, only a small amount of pressure is required to force the particles to new positions. But a high degree of compaction cannot be produced with this high water content, because the thick layer of free water prevents the particles from being forced to force close together. So, when the clay has a higher water content less than the saturation, a thick layer of free water surrounds the particles. So, that with low viscosity acts as a lubricating agent, and under this condition only small amount of pressure is applied, and then the particles will be able to take into new positions in the dense configuration. But whereas you cannot think again with higher the amount of water content, then again water also inhibits the particles coming closer also. They will try to water and air tries to occupy the particles in between this, and it inhibits the process of densification to some extent. So, but high degree of compaction cannot be produced with this high water content, because the thick layer of free water prevents the particles from being forced close together. So, having seen about the typical compaction behavior of cohesionless soils and cohesive soils or clay soils, let us look into a small demonstration. Here I am showing two different types of soils, One is a coarse grained sand, a coarse sand. The other one is very fine grained clay. This was earlier shown, and this is a red clay. Now, as we discussed, if you apply a static pressure to a dry mass of the sand, very little compression is can be achieved, but if you apply any set of vibration, then they will not be subjected to any change in the volume. So, let us try to see by subjecting them to shaking. So, here in this case it is shown here in this mark is the certain state of void ratio. So, when they are subjected to when this soil mass is subjected to shaking in this container for a certain period of time, you can notice the particles are able to take into new positions and arranging into slightly to some extent to denser configuration. So, in this way the delta H whatever we are talking is occurring here. So, in this process of shaking, what we are doing is that to some extent we are expelling the air which is in between the voids of these particles. Now, you can see this has come down. So, that is nothing but the delta H which has caused because of the rearrangement of these particles in a certain single grain state into to a denser state than earlier. Now, let us look contrary to this material, let us look a clay type of soil with certain amount of saturation. You can see even when I subject it to shaking, there is no volume change, because this vibration or a shaking is not enough or not not effective in compacting or in making the soil into a denser configuration. Contrary to this shaking, this type of soils can be compacted easily by applying a static pressure, so that the reduction in volume can be noticed. So, this is a small demonstration which tells the two distinctive behaviors of cohesionless soils and cohesive soils. Now, having introduced the definition of the compaction and then some different distinctive behavior of cohesionless soils and clay soils, let us try to understand about these principles of compaction. So, the early theory which was postulated by R. Proctor in 1930, so he postulated a theory for the compaction and with a laboratory test as well as some modified compaction test, and finally, the aim is to understand the compaction behavior of the soils, different types of soils, and then carry this behavior into the field, so that the soil which is collected from the particular site can be compacted to a denser state, so that it can give the better performance with less settlements and more stability. So, Proctor theory, which is after R. Proctor in 1930, showed that there exists a definite relationship between the soil moisture content and the degree of the dry density to which the soil may be compacted. So, what the Proctor has postulated is that a definite relationship between the moisture content and the degree of the density to which the soil may be compacted. So, that is one relationship he said. Then that for a specific amount of compaction, energy applied on the soil, there is one moisture content termed as optimum moisture content, at which a particle soil attains a maximum dry density. That for a specific amount of compaction, energy applied on the soil, there is one moisture content termed here as optimum moisture content, at which a particular soil attains a maximum dry density. So, every soil will have particularly if it is clay type of soil or a clay sand or a sandy clay, will have a unique value of depending upon the type of the gradation which is there in the soil, it will have a unique value of the maximum dry density or maximum dry unit weight and optimum moisture content. That is the dry density corresponding to optimum moisture content is referred as maximum dry density. So, these two things he has postulated. One is that he said that there is a relationship between soil moisture content and degree of dry density to which soil may be compacted, and then he termed that there is a optimum moisture content at which a particular soil attains maximum dry density. So, Proctor's theory, if you look into it, proposed tests, basically laboratory oriented tests, to determine relationship between moisture content or water content, gamma d dry density. Most of the compaction terminology, it is referred as gamma d is referred as dry density. In principle, it is dry unit weight or void ratio of a compacted soil in a standard manner, and to determine OMC, that is optimum moisture content for the soil. So, if you look into it or if you list the factors which influence the compaction, is that dry density or dry unit weight, compactive effort, and the soil type gradation. So, in the previous lectures we have discussed about the type of the gradation and presence of clay minerals. So, soil type again comes with gradation, presence of clay particles, and gamma d and compactive effort. So, compactive effect is a measure of the mechanical energy applied to a soil mass. So, compactive effort in this thing which is given in this one of the factors is actually nothing but is a measure of the mechanical energy applied to a soil mass. So, the Proctor proposed the test to determine relationship between water content gamma d and void ratio. With that actually it started, and then finally this unique values of dry density and moisture after moisture content will be determined, and then will be used for assessing the field compaction characteristics. So, for measuring the compaction of soils in the laboratory, basically there are two methods are involved. One is the standard Proctor test. It is named after Proctor 1930 standard Proctor test, and modified Proctor compaction test, which we will be discussing in the next lecture. So, standard Proctor test and modified Proctor test is also termed as ASTO compaction test. So, in standard Proctor test, let us look into it. Basically, the scope of this method is to determine the relationship between the moisture content or water content and density of soils compacted in a mold of a given size, mold of a fixed volume and size, with a 2.5 kg rammer dropped from a height of 305 mm. That means that here in this figure, this is the mold and this is the hammer, which is dropping at a height h is equal to 305 mm. So, this method covers the determination of the relationship between the moisture content and density of the soil compacted in a mold of a given size with 2.5 kg rammer dropped from a height of 305 mm. So, what we are doing is that by dropping the rammer onto the soil mass, we are applying a static mechanical energy onto the soil to force the particles to rearrange the particles into the denser configuration or to expel the air in the voids. Shortly we will see how the presence of the water effectively plays a role in rearranging the particles. So, standard Proctor mold and rammer specifications, if you look into it, internal diameter of the mold is 105 mm, height of the mold is 116 mm, 116 mm. Mold has detachable collar and base plate. Basically, the collar which comes because the soil which is compacted in 3 number of layers, particularly for standard Proctor test in a loose fashion. So, initially to keep the soil within the volume, a collar is placed. So, mechanically operated rammer has a face diameter of 50.8 mm, approximately about 5 centimeter, and a free falling weight of 2.5 kg. So, the height of the drop is, these are standard which have been fixed 305 mm. And the procedure is approximately 5 kg of soil is thoroughly mixed with known water content. So, initially we will not be knowing a particular soil can have a unique relationship between a water content or a moisture content and dry density. So, for that to assess the particular behavior, so what we require to do in the laboratory is to take a 5 kg of soil thoroughly mixed with known water content. So, to start with the less water contents. So, weigh the mold without base plate and collar and fix the collar and base plate. So, in the mold compact the weighed soil in 3 layers. Basically, in this standard Proctor test 3 layers are used, giving 25 blows per layer. So, total we have given 75 blows, but each layer is given 25 blows per layer with the 2.5 kg rammer. Weigh only mold and soil after making soil flush with the mold edges and determine the weight W. So, if you by knowing the volume and by knowing the weight, then we will get the bulk unit weight of a soil mass for that water content. So, this procedure has to be repeated by adding the next water content, and then repeating the same procedure. We will have to determine the dry density for that water content under consideration. So, by repeating like this, we will be able to establish a relationship between for a given type of soil, water content and dry density. So, remove the sample from the mold and slice it vertically to obtain the small sample for water content determination. So, here we will take sample for water content determination and thoroughly break the remainder of the material. So, and increase the water content by 1 or 2 percentage points and repeat the above procedure for each increment. Continue this series of determination until there is a decrease in the wet unit weight of the compacted soil. That we have to see, continue this series of determination until there is the decrease in the wet unit weight of the soil mass. The reasons why it decreases and initially why it increases, that we will be discussing shortly. But this is the procedure to establish relationship between the water content and dry density in a laboratory for a given soil. So, compactive energy E applied to soil per unit volume is given as E is equal to NNWH by V. E is the energy which is applied, is expressed here algebraically as NNWH by V. N is the number of the blows per layer. So, in the standard Proctor test it is 25 blows per layer. N number of layers, that is 3 in the standard Proctor test. W is the hammer weight, so it is 2.5 kg, and height of the drop H is 305 mm, and V is the volume of the mold. So, compactive effort can be calculated by using N small n WH by V is around 57,187 kg meter per meter cube or 594 kilojoules per meter cube. We will be able to determine what is the compactive effect. So, the compactive effect which is given in the Proctor test is around 594 kilojoules per meter cube. So, the standard Proctor test procedure of the continuation, if you look into it, the dry density calculations, we knew the volume of the mold and we knew the bulk density of the soil mass at a certain water content, that is W by V. So, dry density of the soil mass can be calculated by using gamma D is equal to gamma bulk by 1 plus W, that is water content. So, with this we will be able to establish relationship between water content and dry unit weight or dry density. So, this particular slide shows a typical moisture content dry unit weight relationship. On the x axis moisture content or water content is plotted, and y axis dry unit weight or dry density is plotted. So, whatever the gamma bulk or gamma dry measured at each water content are plotted here with the points here. So, by joining the points they form a typical bell shaped curve, and here on the right hand side here you will see gamma D, you will see 0 air voids line, which we will discuss later, 0 air voids line with the degree of saturation 100%, and onto the right side of this limb, that is the right side of this point is called the wet of the optimum, and left side of this particular limb is called the dry of the optimum. So, the water content corresponding to maximum dry density is referred as the optimum moisture content. So, this is the combination of water, air which is optimum here with which is referred as a OMC, that is OMC, optimum moisture content, and the density corresponding to optimum moisture content is gamma dry max, that is maximum dry unit weight or maximum dry density. So, here in this slide which is on the right hand side, different molds are shown with different water contents we have tested. So, here this is the procedure how the energy is being applied to the soil mass. So, here the yellow color which is shown here is the face of the soil, on which this is the face of the hammer which is falling onto the soil. So, you can see here like this uniformly the blows have to be given, so that uniformly the energy is transferred to the entire soil uniformly. So, the care should be taken to follow this procedure and also to impart adequate number of blows with the correct drop of the hammer. So, by plotting like this we will be able to establish a relationship between the moisture content and dry unit weight of a soil mass. So, the reason if you observe see here, while before the optimum moisture content the density is increasing, that is what the trend in the density is increasing with increasing water content. With further increasing in water content, you will see that there is a decrease in the dry density. That is what one we should observe. The another thing is that this line we called as 0 air voids or 100% saturation line, and this right side of the limb always on the left side of the 0 air voids line, it never touches the 0 air voids line. That is the particular characteristic of a compaction curve one should note. So, in the principles of compaction and moisture density relation, if you look into it, then again we have to consider the basic how this water which is being supplied to the soil grains is influencing in rearranging into the new positions. So, compaction of soils is achieved by reducing the volume of voids, that is what we have discussed, predominantly the volume of the air voids. So, it is assumed that the compaction process does not decrease the volume of solids or grains. That is the basic assumption, is that compaction process does not decrease the volume of the solids or soil grains. So, here again the uncompacted angular soil grains are shown, and here the compacted soil grains are shown, or uncompacted honeycombed uniform grains are shown, and a compacted uniform grains are shown here. So, compaction of soils is achieved by reducing the volume of voids. It is assumed that compaction process does not decrease the volume of the solids or soil grains. So, if you look into the principles of compaction and moisture content and relationship between dry density and water content, dry density and void ratio, the degree of compaction of a soil is measured by the dry unit weight of the skeleton. The degree of compaction of soil is measured by the dry unit weight. That is what we have introduced before. The degree of compaction of a soil is measured by the dry unit weight of the skeleton. The dry unit weight correlates with the degree of the packing of the soil grain. The dry unit weight correlates with the degree of the packing of the soil grains. So, recall that gamma d is equal to Gs gamma w by 1 plus E. That is what we have earlier derived while discussing about the phase relationships. So, the more compacted a soil, you want the more compactedness for the soil, the less should be the void ratio. The less is the void ratio, the more is the dry unit weight. So, in this relation, if you look, gamma d is equal to Gs gamma w by 1 plus E. Gs is the specific gravity of the soil solids, that is constant. Gamma w is the unit weight of water. So, what exactly we have to look for change is that in the void ratio. The smaller its void ratio and will be, and thus higher its dry unit weight gamma d will be. So, what we try to establish is that the relationship between water content or moisture content and dry density exhibits something like a bell shaped curve. With increasing water content, we are seeing that there is an increase in density, but after certain water content, after attaining a certain water content where the soil is exhibiting the maximum dry density, then afterwards with a further increase in water content, you are observing a decrease in the dry density. So, this is the typical characteristic of the compaction behavior of the soil, where water plays a critical role in the soil compaction process. So, if you look into it, to some extent the reason can be attributed, like the water which is there, it lubricates the soil grains so that they slide more easily over each other and can thus achieve a more densely packed arrangement. So, the water, so without water the lubrication will not occur, the soil remains in stiff position, there will be large amount of air voids. With that, with the large amount of air voids, the soil exhibits large less dense dry density, but with the replacement of the air voids with water, because we are supplying water by increasing the water content. So, by this water also acts as a lubricating agent and softens the clay bonds. To some extent, it helps to arrange the clay particles into the new and dense positions, so that the maximum density of the soil can be achieved. So, while a little bit of water facilitates compaction and too much water also inhibits compaction. That means that on the dry side of the optimum, when you are having water, less amount of water, it is helping you to compact the soil. When you are having more amount of water, it inhibits the compaction. So, in this lecture what we try to understand is that we introduced the compaction behavior of the soil, and in this particular part 1 lecture, and we defined a compaction process, and then we try to understand about a standard Proctor test is one of the laboratory test methods to determine relationship between water content and dry density of a given soil. So, in the next lecture we will continue with the role of water which is played in the compaction behavior of the soils, and try to discuss about other method, modified Proctor test, and other factors like factors influencing the compaction behavior of the soils and field compaction methods.